Yeah, I'm going to talk about event-driven applications with streams and snapshots. And so, who of you actually has heard about Apache Flink before? Let me ask this up front. So, there are quite a few people, okay. So, I would assume that almost everybody would say, yeah, Flink is definitely a streaming framework, but it's not really what I would consider an application framework. So, this talk is kind of a bit of an, let's say, an unorthodox Flink talk. It's not like the standard Flink talk that we're giving. I'm trying to actually convince you of something that might initially seem not super obvious, but I'd like to convince you that actually a stream processor is an awesome way to build online applications, not just streaming analytics. And with applications, I actually mean sufficiently sophisticated applications like services or even entire, collections of services on top of which you run entire websites and so on. Just build this on top of a stream processor. All right, and that, of course, specifically when I say stream processor, stream processing is kind of a general thing, but it comes in various flavors. And when I say stream processing, I usually mean Flink-flavored stream processing. All right, so just to give you a bit of an introduction to stream processing, it's been a paradigm that's, I think, gotten kind of popular in the public, more public mind over the last maybe year and a half. And it's currently, I would say, in its third incantation. Well, that's actually the point I'm trying to make today, right? It started out as something that was more or less of a utility, something that aided batch jobs to compute some more real-time results. The keyword was lambda architecture. It's been something really cool, I would say 3 years ago. I would say over the last year, when you say lambda architecture, everybody says like, that smells rotten. But yeah, that was kind of the first wave of streaming. The second wave was basically streaming systems growing up, being mature, and saying, drop the batch systems. We just do only streaming anymore. It kind of subsumes batch. It's powerful enough to do everything we need to do. And I think the third wave that I'm trying to introduce today is actually streaming being a paradigm for building applications, and in that way kind of merging analytics and applications closer together. And the key point is that I think the streaming architecture, that is the way it has evolved to support data streaming, has actually started to offer pretty unique building blocks for handling two of the biggest problems in building large distributed applications, and that is how to handle large distributed state and how to deal with, with progress of time, with completeness of data, with out-of-order data. Many of the problems that you have, let's say, at least on a low level when building applications, kind of evolve around how to manage large, complex state and how to deal with, data completeness and time and so on. On the high level, it's all news and fake news also, but on the low level, it's usually state and time. Okay, so let's look a little bit into these building blocks and why stream processing actually has some very interesting answers there. All right, so if you start from scratch and say, let me build a new application, something like an application that powers the service for your favorite e-commerce site or so. I think a very common workflow is you start to pick, okay, I have to keep around this state, for users, for shopping carts, for whatever, and it starts with picking a data store, and then the data store kind of influences you on how to pick your data model. Once you have your data model in your data store, this also kind of gives you a few possible ways of thinking about consistency. And then you kind of reason this through and say, okay, this service can maybe assume that consistency, that one, that, and then, in the communication there, it cannot assume anything anymore, but maybe that's not too bad. And then, you start worrying a little bit or testing a little bit your performance, and then you say, okay, damn, I actually have to relax the consistency here a little bit to get the performance, and then everything is kind of in flux again, and you try to redesign it, and it becomes a kind of complicated thing. And in the end, the architecture that you end up with is frequently something that's not terribly simple. It comes with multiple databases, multiple data stores in different forms. It often has something like, like event buses and so on to couple them and have different incantations between them, different incantations or different materializations of the state to make it efficiently accessible. And in these architectures, what we typically see is there's quite a bit of complexity whenever you're working actually against these databases, and you're trying to, or let's say at least this is one that separates writes and reads, so at least here on that side, you have to build a lot of code in trying to make sure that you correctly map the state of the application to the database. If you actually read it very heavily, you may want to introduce a lot of caching and so on, and that just makes the whole architecture very complex, and it's been kind of something that has been, I think, accepted, but it doesn't have to be that way. A lot of the problems in the complexity of building stateful applications come from the fact that this decision was made in many template architectures a while back. You have a compute layer and you have a database layer. And the compute layer is more or less a stateless layer, and the database layer is a stateful layer. If you've been to the talk this morning from Kiki about the event sourcing and Akka, there's actually a very similar point, right? You're trying to say, okay, let me separate that for the sake of, the compute layer is easy. If something there crashes and recovers, it doesn't have to worry about anything, the state is somewhere else. But you're kind of adding the complexity now to the state layer, and you're adding even more complexity to the synchronization of these two layers. So the database layer holds all the state of the application. What's in your shopping cart right now? What users exist, and so on. And every time you want to actually deal with the state, you do remote lookups, you do remote updates, which are expensive. If you want to deal with durability, at least parts of them are frequently synchronous. And if you want to scale this really out, you often have very heavy caching layers. And if you actually think about why that is the case, then a lot of that is just because some working set, some in-flight state of your application needs to be persistent for recovery, right? And there's a very interesting different model to think about that, because what these things that you spend so much effort on to persist them in the database, what these really are, they're just like some variables in your application. So is there a way to just treat them like variables? This is where the model of event sourcing and memory image comes. It's a model that has been proposed a while back, saying whenever you do a change, you do something that would change state in your application, an action like create this, add this to the cart, and so on. What you do is you log it first to an event log, a persistent one, and then you have some process that just operates on these messages. And this process can be incredibly simple. It can actually be just something like a process with some local memory, and it just mutates local variables. You don't worry about any databases on. It's just the variables in your space. It's the simplest thing you can possibly do. The problem is now if this goes away, if you have a failure, what do you do? So this the simple answer in the event sourcing model is, well, it's still in the log, so you can replay. And in practice, that's not a super good answer, because you don't want to replay infinitely. You don't want to retain all the events infinitely in the log. Well, for some cases you may want to, but not in the general case. So what this model typically comes with is the idea of snapshots, right? So once in a while you actually take a snapshot of that memory, just put it aside. And at that point in time you can say, okay, anything older than that snapshot, I don't need this in the log anymore. And on a failure I can just say, bring back the snapshot and replay some events. If you have something that gives you that kind of out of the box, then building a stateful application is really as simple as implementing a function that takes an event, and other than that, you just work with a local variable that is in your Java and your Scala class. And it's not like the fake concept you have with like ORM tools or so, like object relational mappers, where it looks like you're working with variables, but in the end, it's really like a lot of SQL queries. It actually gives you exactly what you expect. It gives you manipulation at memory speed, which means you don't have to go to the length of saying, okay, I probably have to make the database communication asynchronous to scale it. I have to kind of see, if I introduce a caching layer and so on, because it's the best possible thing you can do. Just work on a variable in local memory. Now, this actually, if you just have some single state in memory, worked on by a single thread. Let's make the simplified assumption for now. And this is an incredibly simple model. In practice, what you do often need if you build an application, you need many states with many responsibilities. They're sharded in different ways. You have some state that grows big and that you want to shard by some user ID, another one by article, and so on. And This model can be interestingly extended to just have multiple of these images connected by these queues. And if all of them by themselves actually persist their state, are able to replay any events that had been processed since the last snapshot. And you kind of have the ability to snapshot consistently across all views. So let's say that by the time one of them fails, let's say this one above here, on the top here, this one fails, recovers, and does some replay. It doesn't really affect this one here because the replay is kind of consistently filtered out with other snapshots and so on, so that it reduces duplicates and everything. If you have this ability, then this gives actually a very interesting, very interesting way to build applications where you don't have to spend a lot of effort thinking about like consistency, mapping to databases, state management, and so on. And it also works with very high performance. And this model kind of distributed states and memory snapshots, that is actually almost Apache Flink in a nutshell, right? It wasn't quite actually developed with that use case in mind. It was developed actually with streaming analytics in mind, but it turned out to be exactly like that. It turned out to be exactly that model. And that's why it makes an interesting case, I think, for developing applications. And let's actually go a little bit through what are specific, the low-level primitives that Apache Flink offers there, how this composes into larger applications, and then how this actually contrasts with, let's say, with more traditional architectures where you keep actually state in a database rather than in memory and snapshot it. So the core building blocks in Flink, if you wish, are the four I'm mentioning on those slides: events, state, time, and snapshots. We haven't actually mentioned time even yet, but we're going to go into a whole section about why a good handling of time actually is a very powerful building block for such applications as well. So the core event or compute primitive is just it's just a function that reacts to events, pretty similar to what the fundamental building block in the reactive paradigm is. Together with that, you have in Flink in those functions, if you declare that you want to have state, you have access to state, memory local state. It can come in the form of just let's say a wrapper variable that kind of makes it clear to Flink that this is something that is part of your persistent state, or it can be just any object that you basically register with states and snapshots. It can be literally as simple as a Flink version of a Java hash map rather than a regular Java hash map. On top of that, what you get is access to various clocks in the system. This may not seem super intuitive right now. I have a section on that later, but just as a short summary, there are various notions of time that are flowing through your application usually. One is just wall clock. What's the real time right now? And the other one, what is the event time? What is the time up to which I can be sure that I've seen all my data? In the world of IoT, connected devices, or even not 100% predictable network infrastructures, event as they flow through the system can have certain delays. So at any point in time, when you're computing, it's actually very helpful to know up to which point you can assume data completeness. It may be 12 o'clock in wall clock time, but you may only have seen all events that are relevant. You can only assume 11:55 in terms of having seen all events for that time, right? There may still be some path that is congested and so on that hasn't managed to keep up to process and so on. And there's certain types of events that you really want to process only when you've seen completeness. Let's say you're assembling information about a user interaction session. The event that says, okay, user logged out or it's complete, and let me finalize this bundle and put it to the side. You really want to do this when you say, okay, I've seen the logout event, but I'm also sure that I've seen all the previous interactions. So a very common pattern would be, as you see interactions, you work on them. If you see actually finalizing event, you say, okay, defer me that to the point when actually the system can tell me I've seen completeness up to that particular time stamp that is attached to that logout event. So that is where time comes into play. And then the last one is snapshots. So the function in all its state is actually periodically snapshotted, and that does also take time into account. So For example, actions that you attach to certain points in event time, that's how you, for example, you can use those clocks. You can say, schedule me callbacks for these points in event time. They're also consistently checkpointed. So on recovery, you're seeing exactly the same kind of point in time as well, also point in event time, not just processing time. Okay, so with these basic primitives, you can actually build a lot. It's very flexible. You have events and state and time. It should cover most of the things you want to do. In particular, it's actually a fantastic base to implement a stream processor on top of. So that is maybe a picture that you're more familiar with if you've seen talks from Flink before. It's an example streaming analytics program that takes very simple a set of events coming from Kafka, parses them, keys them by a certain field, in this case a sensor, and then builds 5-second windows in which it aggregates them and then spits out per 5-second summaries. That is actually something you can, if you think about it, very, very easily build on top of those primitives, right? Whenever events come in, you just remember the current aggregate in your state. You treat the notion of time as a progress indicator that tells you when is the 5 seconds up. And you can actually make this 5 seconds on data-driven time, on event time, or on processing time. All right, so when you actually then start composing applications from different functions, like in this case, a source transformation, a stateful operation like the window and a sink, what Flink would do is parallelize them, then basically make sure it attaches this local state. The exact form in which this happens is depending on the implementation of state backend that you choose. It can be something just objects in heap, serialized forms off heap, and so on, depending on what you pick there. In any case, it's with all the state backends that come by default, just local memory. And yeah, then you just push events through it that do mutations and flow through. And at some point in time, Flink triggers basically a sweep of the entire topology and throws a snapshot of that. So it basically doesn't just take a snapshot of the local memory image, it actually takes a snapshot of the entire distributed computation. So let's assume those are, those 4 different types of operators in their parallelism, they can be hundreds and thousands, right? So the scan across that topology will actually take these memory snapshots in such a way that they're all aligned. So a certain event coming from the source is either reflected in all memory images that it affects or in none of them. That gives you a very nice property. At any point in time when something fails, you can just use one of these snapshots and reset the entire topology to it, and you'll actually get a consistency even in the presence of non-deterministic computation, because an event has either affected all of the states or none. So even if you're in a non-deterministic setting and after recovery, some settings are different and you take a different branch in the computation, all states take that branch, not just some of them, which is very, very, very important, I think, as a general recovery primitive. What's even nicer, I think, is that the way that the state and the individual operations work with each other is they're kind of loosely matched. On every recovery, a state is matched into the operation, which allows you to actually change the data flow of computation between different runs. So if you have actually a snapshot and you figured out, I actually need to maybe change the program a bit, make it a little more complex, add another, pre-processing step here or there, you get a changed data flow, and you can actually take the state and match it into that changed data flow. Within reason, naturally, the state needs to somehow be compatible. The changed data flow should still assume that kind of state. So if you're storing a hash map of user IDs and JSON records, then the resuming topology should not assume a graph or something like that, right? So it needs to be kind of compatible shapes of state, but the structure of the computation around the state is pretty flexible in the way it can change. And that is again a pretty neat primitive, because it allows you to basically say, hey, let me do some IB testing. I just take a snapshot of one application, I modify the code a little bit to be a bit different, and then I bring it up from a snapshot. And it kind of resumes exactly where the other one left off with different code. And if you think about it like that, you almost have a lightweight CQRS architecture. For those that visited the event sourcing talk in the morning, You will have heard this term before. It's a command query responsibility segregation. It just means that you build your system in such a way that the way you write and manipulate state is completely different modules and completely different code from the way you basically read and compute the presentation that you give back in the application. So this is kind of a very compact way to do it, right? You just need one event log at the beginning, let's say something like Apache Kafka, where you persist all events. And then you can have basically a lot of individual states that you derive, some states just as basically the authoritative ground truth of what is the state in your application, and some other states that are just computed, like as a utility to be exposed on the read side. And you don't actually need any intermediate persistence because the snapshot algorithm will actually be able to replay also later states from previous states and the initial events. So you don't need to actually save many event logs in between different computations. The reads can, in theory, go directly against Flink because there's a component, there's a module called queryable state, which allows you to actually expose state from within processes. And when you want to access it, and even if the state is sharded, the queries will actually figure out on what shard is important for you and actually route the queries. What you can also do is just mirror the states that you've computed for reading into an outside database. And that actually is a much simpler thing to do than maintaining the state directly in the database because we're not ever reading in your write model the state from the database, so you don't have any consistency issues, right? You're just reading the authoritative state from your memory, and the only thing you're doing is you're mirroring changes or aggregated changes out to a database. All right. So let's look at a few of the neat advantages that this has actually about or over like working in a traditional way with compute and a database. So you can think of the picture. You can think it changes like that, right? You have state and database, and the database has the application state, and usually also long-term data like older application state. In an architecture based on streaming and snapshots, you usually just have attached local state, which is maybe just the local memory, and then you have a storage port which stores you the streams, let's say in a Kafka topic, and some snapshots. For snapshots, you may want something like S3 or HDFS, or just some file system where you can put some snapshots. So performance-wise, this has some very interesting implications, right? So where the separation of compute and state with stateless and database actually crosses the tier boundary between compute and state. Very often, the streaming architecture basically does state modification almost entirely locally, and the snapshots are large writes that are written out, and the interesting thing is these snapshots can be persisted completely asynchronously, right? You can basically say, take me a point in time snapshot. You can make this a more logical operation, like if you have copy on write data structures, you don't actually take a copy. You just kind of mark the state and say, whenever I modify it from now, I need to slightly copy it. So you can actually take an immutable variant as a logical operation, and then you persist this in the background. So all this movement between the tiers are moving of large chunks in the background. There's no synchronous component involved. The consistency model is by itself quite interesting. It's not totally comparable because if you have a shared database, different states can easily, communicate with each other by just updating certain keys there. This is kind of a pattern that is not quite possible to replicate in that architecture, but it's also kind of discouraged pattern, I would say, because if multiple states compete for the keys, then then it becomes a transaction hotspot. So if you actually manage to kind of map this into multiple states and you send updates around as events between these different states, then this gives you a very nice consistency model because each operation on an individual state is what has become called exactly once in stream processing. So even under failure and recovery, the state is going to reflect each operation exactly once. There's a single writer to each shard at each point in time, so there's basically no transactional races between multiple writers. You cannot have stale reads. It's just not something that can happen in this theoretical model. Per individual state, exactly once guarantees, and across states you get this kind of. It's not quite what is called snapshots consistency in distributed databases because it's a different model, but you can get something similar. For example, it is possible to say, hey, I want an application to only be able to access something that has been stored as of a successful snapshot. And then it will basically see in all different states only data that is part of a successful aligned snapshot. So an event is either reflected again in all of the states or in none of them, which is kind of close to snapshot isolation. It's not quite the same, though. Scaling such a service is, I think, a very simple primitive in this world, right? Let's say in the more traditional architecture, if you scale one, you provision compute. This is usually the easy part, right? I think this is why this architecture came up with, because provisioning compute becomes easy. But provisioning state is actually where you move the problem to, right? You have to start scaling out the database, which is way less trivial, right? In the streaming architecture, you basically just scale the compute and the state together. And on the snapshot store, you may just need a little bit of additional storage in the file system. And a very similar thing is actually just provisioning a new service, starting a new service. You don't have to actually create a database or provision database capacity. You just have to launch a few containers and reserve a little bit of snapshot storage. Something that is also a very nice property is I think that every service kind of doubles as a batch job, or every application doubles also, or can double as a batch job. Let me explain what I mean by that. Let's assume we have a stream of events. We have an application that computes something, and then it mirrors out some state into some external data store. And it just so happened that at some point in time, we did have some corrupt events in the input, or we did have a bug in the application. So what actually happened for a time, we computed some wrong results and mirrored them to the external database. And now we have that in there. So we can, in theory, just say, hey, we have an earlier snapshot. Let's just roll back the entire thing and recompute everything. That's definitely possible, but not everybody may want that, because the live service should not actually be ever reset or rewound. It needs to be keeping up with the latest events. So you can just create a copy of that and, let's say, run it over a backup of the data that you have from the last days. It can be the same stream if you still have the events in the event log, or it can be a backup of the data in HDFS. And the same code can run over this copy and actually mirror again its results into the database and kind of repair the external state. So by just modeling it as an event-driven or as a streaming application, you kind of get the point that each application is also a stream processing application, right? And since a stream processing application is by transitivity also a batch processing application, you can almost think that each application also becomes kind of a way to repair itself if just run over a copy of historic data. The whole concept of snapshots is actually powerful in that you're not restricted to just have one snapshot of the application at a time. You can actually say, I'm starting out with application A, taking a snapshot. By the way, we call these save points in Apache Flink. Then I'm taking another one. I'm using actually that snapshot to bring up a B variant of the application where I'm trying to tune my recommender model a little bit, see if it is a bit better. I'm running this. It looks kind of good. Let me take another snapshot, fork a C variant. And at that point in time, I see, okay, maybe B was the best one, and then I just can A and C, But I still have a tree of versions of snapshots that kind of relate to each other. This kind of is a very nice way to also realize blue-green deployments. So if you want to try out new approaches or new features, if you have a blue-green way of doing things, this means you're running two installations concurrently. It's a bit like A/B testing, but it's usually the terminology you do if you say you upgrade code or frameworks and so on. So you bring up temporarily two variants of the whole application. The second one that you bring up just starts from a snapshot that was taken from a recent snapshot taken from the other application, and once it's caught up, you can basically stop the first application. So if you ever want to upgrade the framework or your code, that's a very simple way of doing it, right? Just start a second copy of the application from a snapshot that was just taken from the previous application. All right. Enough about state. Let me quickly lose a few words about time. So handling time in these systems is, I think, quite a tricky thing. I think it's very hard to make a statement how these things are handled in, let's say, in non-streaming, non-event-driven kind of applications, because I think it's very custom to each application. The streaming architecture here has a few interesting building blocks, and this is the event time clocks that allow you to basically always ask the system, hey, up to which point can I consume data completeness, and hey, give me a callback by the time you think data is complete as of that particular event time. What does that mean in particular? So first of all, we have to figure out what kind of time we're talking about, and there are various times you can talk about in such a system. Proper event time, when was an event generated, basically marked by the timestamp that is attached to the event by the producing device. Broker time, when did it first enter, let's say, my data center, when was it first persisted in the message queue. Ingestion time, when was it first picked up by the first part of my application. And then actually processing time, when did it reach the actual operator. In an ideal world, these are all very close to each other, and it shouldn't really matter that much which one you refer to. In the practical world, they can differ a lot. The last two, if your system is well behaved, are close to each other, but event time, broker time, and let's say processing time can differ a lot. There's kind of a, and it makes sense to actually, in your application, be aware of all of them, at least if you're building a service that is dealing with real-time events and wants to be able to also handle cases like IoT, sensors, disconnected devices, and so on. And here's my favorite example to explain why. So let's assume we're in the Star Wars universe, right? And we have events that are happening in that universe that happen in a certain chronological order, right? So, for example, there's the first time when Anakin is born, and then he has all these issues, and he turns evil. Then there's the rebellion. Then Han Solo gets frozen, and the second Death Star gets destroyed, and all of these things. So there's like a semantic order of those things. But also because in that universe they're destroying suns and stars and planets all the time. You get these huge distortions, and we actually get the information, or we observe them at vastly different points in time. So we just happen to observe the New Hope way actually before the Phantom Menace or so, right? Just because of different travel delays. And now what do you want to do if you're like an application that processes these events and that observes them like that? And that's really kind of up to the application. I mean, if you're really interested in maximum semantics, you probably want to process them in order, and you may want to say, okay, I defer some form of processing until I can come to this event and it makes sense. But also, if you're interested in a bit of a real-time characteristic, you may not want to do this, right? You don't want to be the only person that has not watched Star Wars in 1995 just so because you say, no, I'm not going to watch it before I have seen the beginning of the saga or so, yeah? So there's kind of a merit to both of that, right? Keeping a little closer to real-time or paying more attention to semantics. And often it's a blend and a trade-off, right? And then, of course, there's special ways of saying, okay, I want to actually, treat them in semantical orders, but only up to a certain threshold, and there are special paths or special ways to classify late events and treat them differently. So you can mix this in all ways. All right. So what does a framework like Flink actually offer to do that? So it offers you it gives you tools to build these watermarks. Watermarks are basically points in the stream where it says, okay, event time has progressed to that particular instant. So watermark of time 20 says, okay, all events up to time 20 have been seen right now. Or let's say a watermark of time 12, 55, and 39 seconds and 500 milliseconds says that the framework's pretty confident that all events up to that point, events with timestamps up to that point have been received. And you can use this to make an assessment of completeness. Now, how good that assessment is in the end depends on how good you can generate these watermarks. In many cases, you can generate them very well. In other cases, it's a little harder. But in general, they're an extremely helpful building block. For in-order streams, they're kind of a trivial thing. If timestamps are ascending, their meaning is kind of trivial. But in out-of-order streams, they're very important to establish within the event stream exactly these points. Like I can assume completeness up to time 17 or so. And Flink will organize them for you in parallel, right? So reading events from the source, at some point you do generate these watermarks. Let's say you're picking them up from Kafka initially, and you're dealing with broker time or ingestion time. So you can actually in each parallel instance declare progress very easy. And then Flink does the work for you to say, hey, if events are routed multiple times like this, and then this operation is waiting for input from here and there, and this one has made the progress, and this one has not made the progress yet, so I can only assume so much here. It will kind of figure these things out for you and give you at every operator the information to say, okay, this particular parallel instance of compute and state can assume that progress of time. All right. So those are kind of the building blocks we have there. For stateful event-driven applications, you can build applications on them typically in the event sourcing or a CQRS pattern, or you can use this to build stream processing on top of. And I've said it before, stream processing in our view kind of subsumes batch processing because streams are the more general thing, right? Streams are data that flows and is potentially unbounded. If you have a batch, it just means that you're defining a beginning and an end at some point in time. Like, for example, if you ingest your data from your web server and you have rolling logs per hour or so, then this is really just a window of that stream, an hourly window, right? If you can process the infinite one, then you can also process the finite one. It's actually the simpler problem. All right. So how does it actually look to use Flink? So there are multiple layers of abstraction in Flink. The one at the lowest level is exactly what I've been describing here. It's just called like a process function, which is a function that just processes events, maintains state, treats time. Snapshots are not in here because snapshots is kind of, if you wish, an operational aspect. It's not an aspect of the API. It's an aspect of operating the system, of recovery, of migrations and so on. On top of the low-level process function, you have an API for stream and batch processing actually both together. That gives you a view of streams rather than individual events, and higher-level primitives like windows, tumbling windows, sliding windows, session windows, and so on. The typical things that you may want to do on streams if you do streaming analytics. And on top of that yet, there's two APIs that are basically purely for high-level analytical processing, which is the table API. It's an API built on the concept of dynamic tables, and Stream SQL. Let's quickly look at how all of these abstraction levels look like if you process them. So this is a piece of code from a process function. It's just, in this case, a class in Scala. You can see there are a few points. For example, at this point here, you just declare a variable, a value state count with timestamp. It's just a way to say, hey, I want to maintain a count with timestamp, and I want to make sure the system knows that this is part of my state. You can also define it in a different way by just saying declare your field and then register it in a different way. It's just a way of letting Flink know what this is. We're not literally taking images of the system memory, although that would be a kind of cool thing to do, but it doesn't really match Java really well because the memory images changes all the time when objects move due to the garbage collector. There's really no point in doing that. Then there's the second part. This is process element. This is something that reacts to every element invocation, and it gets the event, it gets a context which allows you to access state, access timers, register timers. And what you can then do, you can just execute some code on your current event and the value of the state, collect, output some events, update the state, register some timers, and you can define callbacks for timers. The important thing is that even though this looks like a wrapper, it's kind of a simple wrapper. It's really just a pointer. When you access that value, really access it from the local memory. It's not like a thick wrapper like ORM or so that actually goes to a database and fetches it or anything. This object exists in your memory. It doesn't exist anywhere remote. All right, the streaming API, we kind of saw it on a previous slide. Concepts of streams, second kind of higher order functional programming. And then the abstraction level one up from that is dynamic tables and Stream SQL. So dynamic tables are, let's see if we have some extra time in the end, I can actually try and explain this a little bit. Dynamic tables are tables derived from streams. For those of you that are familiar with Kafka streams, there's like this concept of a K table. It's just a table from a changelog. Dynamic tables are kind of a bit of an extension of that with a way of, as you convert streams and tables, you kind of turn the whole processing into the processing from streams into a processing of diffs. So whenever the table changes, the table kind of emits a diff to the changes, and then all operations actually compute on these differences that the table emits. So in the end, what flows in the computation are not records, but just actually messages that say, hey, this should be added downstream, this should be removed from downstream, this should be updated downstream, and so on. So it's kind of a way to turn SQL into a differential computation. All right. I think with that, we're quite good in time. The closing remark that I want to make, I hope I could actually convince you a bit that this is where we're going to. So streaming analytics and event-driven applications are two sides of the same coin, I would say. They have been treated very differently, but that is mostly an artifact of like architecture, software, and so on. With the right design patterns, with the right kind of frameworks, they can actually be extremely similar or ultimately even the same thing. And with that, stream processing is actually an awesome way to build applications. You can think of stream processing just as an event sourcing CQRS pattern on steroids, because it gives you a lot of things out of the box that are very easy. For example, snapshots, exactly one semantics, alignment of snapshots, replay time, and so on. All these things kind of work just for you. You don't have to worry a lot about that. All right. Here's a shameless plug at the end. If you're actually interested in this whole stream processing, content, there's another conference in another awesome European city that is dedicated to that. If you're interested in just learning about it, or if you're working with stream processing and want to share experiences, feel also free to submit some abstracts there. And with that, I'm done. Thank you.